Good morning, ladies and gentlemen. My name is Asri Ulfia. I am currently taking Masters in Department of Electrical Engineering at Institute Technology 10 November. Thank you for the opportunity to presenting my research project entitled Recognizing Medication Label System with Audio Output for Individuals with Visual Impairments. Let me begin by explaining the background and motivation behind this project. According to the World Health Organization, over 285 million people worldwide experience some form of visual impairments, from moderate vision loss to total blindness. This condition significantly affect daily life, limiting communication, mobility, and access to information. One critical issue is the inability to accurately identify medication. Most packaging use standard printed text, and although some include brailles, many visually impaired individuals cannot read it, increasing the risk of medication errors. Studies show that about 30% of blind individuals have experienced medication related mistakes, including overdoses. This highlights the urgent need for a smart, accessible system that provides essential drug information in an understandable format. Now that we understand the problem faced by individuals with visual impairments, let's move on to the objective of this research. This research aims to develop an intelligent system that enables blind users to independently recognize medication names from strip packaging. The goal is to offer a low-cost, real-time, and offline-capable solution by combining three main technologies. But the first one is YOLO-VX. You only look one version egg, an object detection algorithm that finds areas containing text on the medication packaging. The second is EasyOCR, a lightweight and flexible optical character recognition tool that extracts text from the detected regions. And the last is PyTTX X3, a text-to-speech engine that runs offline and speaks out the recognized medication names to the user. By integrating these three, the system allows user to receive information audibly without needing assistance. Here are some relevant research supporting my project. While previous studies mainly focused on identifying drug names visual or extracting text using OCR, my research extends the functionality by adding an offline audio output. This allows visual impaired user not only to recognize medication independently but also to hear the result in real time without needing an internet connection. It offers a more complete and accessible solution for medication management. To achieve this goal, we designed a system that integrates several technologies. Let's take a closer look at how the system works. As shown in the flowchart, the process began when the camera was turned on. The system started by detecting objects in the camera's view, particularly looking for medication packaging. Once a packaging object was identified, an image was captured for further analysis. This image was then processed using the YOLO-VX model, which identified specific region containing text. These regions were extracted and sent to the EasyOCR library, which converted the image-based text into a digital format. After the text has been successfully recognized, the system converted it into the speech using the PyTTX X3 text-to-speech engine. The generated audio was then played through a speaker so then the user could hear the name of medicine. After the audio was then played, the system checked whether the process was finished. If no, it repeat the steps from the next for the next input. Otherwise, the system ended. With the system structure in place, the next step was to prepare the dataset needed to train the model. The dataset used in this research consisted of 1623 images of 8 types of medication packaging: allopurinol, dimacolin, mefenamic acid, metformin HCl, paracetamol, paratusin, plantacid forte, and simvastatin. These images were captured directly using a Logitech C270 webcam. Annotation was conducted using the RoboFlow platform by labeling text regions within each image. To enhance dataset diversity, data augmentation was applied by adjusting lighting condition by -20% and +20%, which increased the dataset size to 4837 image. The final dataset was then converted into the YOLO-VX nano format to support the training process. Once the dataset was ready, we proceeded with the model training. Here are the results we obtained. The YOLO-VX Nano model was chosen for its efficiency and suitability for a lightweight application and was trained for 100 epochs with a batch size of 32. The number of epochs was determined based on observation during the training process and was deemed sufficient to enable the model to learn pattern comprehensively without overfitting. Following the completion of the training process, the model achieved an accuracy of 91.84%. After training, we evaluated the system performance through testing to ensure its effectiveness. The system was evaluated using a laptop connected to a webcam. Testing showed that detected remained effective even when the image were angled or rotated, demonstrating flexibility in handling various image orientation. The average processing time for entire system was approximately 4.5 seconds, with the YOLO VX model accounting for the majority of the time, around 2.9 seconds, while the remaining stage EasyOCR and PyTTXX3 complete it under 2 seconds combined. Timing evaluation conducted across different types of medications indicated that the system maintained stable performance and operated within an acceptable time frame for real-time implementation. Based on the training and testing outcomes, we can now summarize the key findings and impact of the system. Medication management remains a major challenge for individuals with visual impairments. The purpose system combining YOLO VH, EasyOCR, and PyTTXX3 offer an effective solution by enabling independent access to medication information through computer vision and audio output. With a training accuracy of 91.84% and average response time of 4.5 seconds, and system demonstrates strong potential to improving both safety and autonomy for visual impaired users. While the results are promising, there is still room for improvement. Let me share some recommendations and for future development. To further improve its practicality and impact, it is recommended that future development focus on optimizing processing speed, expanding the medication database, and adapting the system for mobile or wearable platform. This enhancement would support broader adoption and provide more accessible real-time assistance for individuals with visual impairments. That concludes my presentation. Thank you very much for your attention.